differentiation for y equals to fx, which is a curve drawn in black, the derivative f dash x or dy by dx is the slope of the tangent to the curve y equals to fx at point x. This black curve is y equals to fx, and there are 2 points on the curve P and Q. At P, the value of x is, the value on x-axis is x, and the corresponding value on y-axis is fx. Likewise, for Q, the value on x-axis is x plus h, and the corresponding value on y-axis is fx plus h. This line PQ is a secant or a chord. So I can say the secant line through P and Q has slope fx plus h minus fx over x plus h minus x. Now this is just according to y2 minus y1 over x2 minus x1. You are already familiar with it. Let me write the coordinates. The coordinates of P, the x value is x and the y value of P is fx. Likewise for Q, the x value is x plus h and the y value is fx plus h. And if you apply y2 minus y1 over x2 minus x1, you get this expression. And if I simplify the denominator, x and minus x will cancel out and I'm left with h. Now in order to make this secant line or chord as tangent, I have to minimize the value of h to 0. If I do so, the point Q will come at point P. So we can approximate the tangent line through by moving Q toward P by decreasing h, of course. And let me introduce the concept of limit. In that case, I can say my value of h will approach to 0. So the secant line will become a tangent when h approaches to 0. So it is limit, this is something very important, and I'm using the concept of limit that h approaches to 0 for the above expression. So this thing will become f dash x, and this is actually a formal definition which is new in the syllabus, but a very brief description is required. And of course we can derive all the basic differentiation formula using above a definition. This is the definition of differentiation, which is new in the syllabus. Now in order to move on, I use some simple concepts like for simplicity I can say d by dx, which is of course a derivative, is an operator, and this operator follows certain rules. The first rule says that derivative of a constant number is 0, derivative of x is 1, derivative of x power n is like power come first, the power come first, and whatever power of x, you will subtract 1 from there. So it is nx n minus 1. And if something is multiplying, then that thing will remain as it is. Mind it that in rule number 1, if constant number is without any x, then it will become 0. But if this some constant number is coming with x, then it will not become 0 like this. Like in case number 4, you can see a is multiplying with x power n. So a is still there, the power is coming first, and you will subtract 1 from the power. I can show you some examples. Like in example number 1, I have an expression y equals to 2x cubed minus 3x squared plus 4. Now if I take derivative of this y, so the 2 is multiplying with x cubed, so you can see 2 is as it is, 2 is coming as it is, and I'm only taking the derivative of x cubed, following the rule. Power come first, 3 is coming first, and I will subtract 1 from that power. So this will become 3x squared. Then I will move to the next term. Minus 3 is multiplying, so it remains as it is. I will take the derivative of x squared, power come first, and power minus 1. So this will become 2x. A constant number without x will become 0. On simplification, I get this as my answer. I can show you a bracket case. Suppose my y is cube root of x squared plus 2x. Now I can write this thing as x squared plus 2x raised to the power 1 over 3. This is a little bit more simplified. If I take the derivative of this y, then dy by dx is power come first. You can see this power 1 over 3 is coming first. I will copy the bracket, this bracket over here, and power minus 1, 1 over 3 minus 1. Then I take the derivative of inside the bracket. X square will become 2x and 2x will become 2. I can simplify it further. 1 over 3 minus 1 will become minus 2 over 3, and this is my final answer. Another case, suppose there is another expression in case number 3. Suppose a, variable a, is under root 3 over 2x squared plus 24,000 over under root 3 x raised to the power minus 1. Now when I take dA by dx, I will only take the derivative of x squared. Since under root 3 over 2 is a constant number, so it remains as it is. Derivative of x squared, power come first, power minus 1 is 2x. This constant number remain as it is, 24,000 over under root 3. I will take derivative of x raised to the power minus 1, power come first, power minus 1, so this will become minus 1 multiplied by x raised to the power minus 2. On simplification, you get this as your answer. Applications of differentiation. Number 1 is a rate of change. Whenever in calculus you see rate in your question, it means it is something over dt. In calculus, rate imply dt. Suppose y equals to fx is your curve, then dy by dt is rate of change of y with respect to t. And dx by dt is rate of change of x with respect to t. So likewise we can go dv by dt, dr by dt, there could be other variables as well. But rate always stands for something over dt. In this type of question, we have to apply chain rule, which is this. dy by dx is dy by dt divided by dx by dt. We can write this chain rule in this way. Dy by dx is equals to dy by dt into dt by dx, dt get cancelled out. At the end of this lecture, I will give two examples in which I try to clear this thing more clearly, how this rate apply to a question. So move on. Concept of gradient. If y equals to fx is a curve, then dy by dx, which means derivative of y with respect to x, is a gradient function. Gradient function is always in terms of x, and if you write some particular value of x, like in this case I'm taking gradient at a particular point p coordinates x1 y1, then I get a particular value of f dash x, that is the gradient of the tangent at that particular point. There is a relationship between gradient and angle, and it is important. Like if you look at this figure, this line is a tangent, and this tangent is making angle theta with x-axis. Now what I'm trying to say here, that tangent theta is actually derivative at some particular point x1. Now you can see in this case point x1 is the coordinate, is the x coordinate of p. So at a particular point, if you take the gradient, then that gradient is equals to tangent theta, where theta is the angle between the tangent and the x-axis. Now equation of tangent and normal. Tangent is a line which touches a curve at one point, and normal is a line, a straight line, which is 90 degree to the tangent. In this blue curve, I am taking a particular point P, coordinate x1, y1, and I am showing you the equation of tangent. Equation of tangent is simply equation of a straight line. So at point P, x1, y1, equation of tangent is y minus y1 equals to mx minus x1, where m is the value of dy by dx. Value of dy by dx, you always get a number since you are specifying a particular value of x, so you will not get a function, you will get a value. Equation of normal at point P, x1, y1, slight difference, normal is perpendicular to the tangent, so the equation is y minus y1 equals to minus 1 over m x minus x1, where m is the same thing, same value of dy by dx at point P, x1, y1. Stationary points or turning points, suppose you have a curve y equals to fx, then in this figure you can see A is your maximum turning point and B is your minimum turning point. We call these turning points as stationary points because the value of tangent is 0, the gradient of tangent, is 0 at these 2 points. So suppose the curve is not drawn for you and you have to decide the coordinates of stationary points, then using calculus you can do so. You take dy by dx, first take dy by dx, put it equals to 0, find dy by dx, put it equals to 0, you will get the value of x. You can plug in the equation of the curve and get the corresponding value of y. Since your y is a function of x, y equals to fx, it is always given to you. So we get the corresponding value of y. Now as I have drawn over here, stationary points could be maximum or minimum. A is a maximum turning point, B is minimum turning point. So using calculus you can even find out whether the turning point is maximum or minimum. So what you do, you will take derivative of the first derivative, like Um, if y equals to fx is your curve, then dy by dx is your first derivative, d2y by dx squared is your second derivative. In the second derivative, you will plug the value of x. This x equals to x1 you are getting through your stationary point. So when you plug the value of x1, value of x as x1 in your double derivative, then either you get the double derivative less than 0 or you get greater than 0. If the value of double derivative is negative, is less than 0, then the stationary point is maximum, and if it is positive, then the stationary point is minimum.